Here's the final part for the method of Laplace transforms. What we've done so far is we've taken a function. We'll just assume that the natural variable is t, although traditionally it could be x's also or other things. And we've done the Laplace transform to turn that into some other function which we used a different variable for that traditionally we call s. Now what we want to do is to reverse the process. We want to find the function of t when we know the transform. If you recall, back in Calculus 1, we did something similar. If we know the Laplace transform of something, function of t, is some function of s, then we know that the inverse Laplace of the function of s has got to be the function of t. We did this, for example, back in Calculus 1. If I knew that the derivative of something like ln(x) was a 1 over x, then I knew that the integral of 1 over x was the ln of x. And so we have the same idea here. We have done the transform. We have done something to f of t and generated an capital F of s. Now we're going to just recognize how we can get back from some f of s to the f of t. Now here's some that we've already done. Back in chapter 23, the first transform that I showed you using the definition of Laplace transforms was to transform a 1 into a 1 over s. Well, if we know that, then we know that the inverse Laplace of 1 over s is 1. We did this one back in chapter 23. We transformed a t into a 1 over s squared. That means that the inverse Laplace of 1 over s squared must be a t. This is a similar one to what we did back in chapter 23, only I used a k instead of a 3. And that just says that the inverse Laplace of 1 over s minus 3 is e to the 3t. Now let's see how this works. If we're trying to find the inverse Laplace of 4 over s minus 3, what we want to do is to find something in the table that resembles 4 over s minus 3 in the transform columns. So if we look through these columns, we want to find something that 4 over s minus 3 can be made into. And then, of course, we'll look back to the left side to see what function that came from. Here's how that would work. You notice that the 4 over s minus 3 is the same as 4 times the inverse Laplace of 1 over s minus 3. Well, the 1 over s minus 3 matches this. If the a were a 3, then it would be an exact match. So we assume that a is a 3, and we convert that into the function of t, which would be e to the 3t. Now we still have the 4 on the front. Now again, here we look in the table for something that sort of resembles this. Now since it's an s to some power bigger than 2, then we know that this is going to be something that looks like this. Now there's an n factorial that we'll need to take care of. So s to the n plus 1 sort of implies that n would be a 3. If n were a 3, then n factorial would indeed be a 6. So everything matches up for this to be a t to the third. Here in the table is something that resembles what we're looking at. And we notice that for the s squared plus 16 to be an s squared plus a squared, then a would have to be a 4. Well, if you look in the top, a is indeed a 4. So everything matches up nicely to give us our sine of 4t. Now I chose one here that intentionally looks a lot like the one we just did, just to emphasize that here, if we've got a 1 over s squared plus 9, that is, again, in a format similar to number 7 on my table. Well, for this to happen, then the a would have to be a 3 in order to have an s squared plus 9. But that also means that the top would need to be a 3 in order for it to match. Well, it's not a 3, but we can make it a 3 by multiplying by 3 and by 1/3. We multiply by 3 on the inside, we multiply by 1/3 on the outside, much like what we did when we were doing integrals. And so we end up with our inverse transform. Now, let me point out on this example that we have s, top and bottom. That is not the one that we were looking at a while ago, because there's no s in the top of that one. So, trying to match this up, you notice here is the one that's similar. S on top, s on bottom. And so let's see if we can get things to match up. Well, first off, s squared plus 4 and s squared plus a squared tells us a would have to be a 2. In the top, there should be just an s, and we have an 8. Well, again, because the Laplace transforms are linear, we can take the 8 outside of the transform. And so now the s over s squared plus 4 is a direct match for the cosine of 2t. Now, at the end of chapter 23, we talked about this, the fact that we've got an s minus 6 to the 3rd power implies that we have a translation. Now, here's how we'll handle that translation with a little bit of extra symbolism, I guess. We notice that we can take out an e to the 6t, that's the s minus 6 part, and now we just need to do the inverse Laplace of 1 over s cubed. Well, the inverse Laplace of 1 over s cubed comes from here, number 3 on our chart, and in order to be 1 over s cubed, n would have to be a 2, and in the top, 2 factorial would be a 2, so in order for this to be transformed, we'd have to have a 2 on the top. And so we multiply the top by 2, we multiply out front by 1/2, and so the inverse Laplace of 2 over s cubed comes out to be t squared. And so we put those together and we end up with an e to the 6t times a 1/2 t squared. Okay, now that we've learned how to do inverse Laplace transforms, let's see how to put this all together to solve differential equations by the method of Laplace transforms. Again, you can print this screen out if you want that in your notebook. Step 1, do the Laplace transform. Now this problem is actually one that we did in chapter 23, I guess. And so the Laplace transform on y double prime plus 4y equals 20 e to the 4t. We do the Laplace transform on the y double prime. We do the Laplace transform on the e to the 4t. Put all of that together. Solve for the Laplace of y. And again, this is exactly the same one I showed you back in chapter 23, so that's why we're going through it quicker. Now this is where knowledge of the Laplace table comes into play. We need to know what things look like so we'll know where we're headed with this. And we've already done a few inverse transforms, so you know, like right here, we don't have any transforms that have an s plus something over an s squared plus something. So we can split this apart into two separate fractions. Also, I showed you this back in chapter 23. This doesn't look like anything anywhere in our table. We need to split this using our partial fraction decomposition or our Ch25. Some of those will combine together. And so this is in the format of the things that we see in our table. We need to find the inverse Laplace transform of each term of that expression. So, again, we look in our table. I'm not going to pull up the table and do all of this, but you can verify by looking in your table. The inverse Laplace of 1 over s minus 4, the inverse Laplace of s over s squared plus 4, and the inverse Laplace of 2 over s squared plus 4. And there is our final answer.